You ready, guys?
Yeah.
Shall we work out how fast light travels?
Yeah.
Yeah? Because light's got a speed. Do you know that? Some people call it light speed. It's really, really fast. Right, to work out how fast the speed of light is, we need 6 things. A plate, a little bowl, some chocolate, a ruler,
And a plate.
microwave. Yeah, I said a plate. That's the first thing I said. Plate. And a calculator, which I'll get after. Right, so first we have to do a bit of deconstructing on the microwave. Did you know, guys, when you cook something in a microwave, the food turns around, yeah?
Yeah.
It goes round and round. You knew that? Yeah? Well, we don't actually want that. So we take that out. Put that down. And we take this out. Alright. Pass the bowl, please, Ken. Yep.
I think that's made of glass.
It is made of glass, that's right. So we put the bowl, this is what makes that spins around and then drags the glass plate around with it. So if we cover that up, like so.
Not touch.
Alice, can we leave that, please? Thank you. Ken's quite right. And then, look, so I put the bowl in there. Can you see, Ken?
Yeah.
Yeah. And then we put the plate on top of that. And now, if I make the microwave work now, it's not going to spin. Okay? Because we don't want it to spin. What I do want, though, is that chocolate, guys. Alice, can you take the chocolate out, please?
Okay. The whole piece?
Yeah, take the whole thing out.
Okay.
It's a big piece. No, open the wrapper more. Sweetie, open the wrapper. No, stop. Like this, see? The wrapper's open. Now we can pull it out. Don't put your hand all over it. Okay, pass it to me. Pass it to me.
Wow.
Thank you, sweetie.
Look at
Do you wish you could eat all this? You, guess what? You're not. Alright, so put the chocolate on the plate, alright? Now we're going to actually turn the microwave on. Okay, guys? Shut it. Right, let's give the microwave, I don't know, let's go for a minute. Now, the chocolate is not spinning, which is a key part of this. We need it to not spin. Just going to heat it for a little while, okay, guys? I'm not actually sure how long. So, what we want is for some parts of the chocolate bar to start getting soft, maybe start melting a little bit. Okay, so we can open the microwave soon and just check. That's 40 seconds. Let's have a look. Oh!
it has holes
Look at
in
that!
it.
It does! That's what we want. Okay, so 40 seconds was plenty. Alice, off your chair, please. I need to get her out. Thank you. Ken, come and have a look. Alright, bring your chair over.
It smells nice.
Of course it smells nice. It's cooked chocolate. That looks a bit funny, doesn't it?
Yeah.
What we need to do is measure, Alice, with the ruler. We need to measure from the middle of this hole over to the middle of this hole. So don't actually touch the ruler on, just put it above the chocolate like this, okay? Alright, so, come on phone, focus, there we go. So that's about 12 centimeters, okay?
Yep.
Now that's a number that we can use in a calculation to work out how fast light travels. Okay, let's work out the math now to come out with the speed of light. Now don't stress, it's not hard math, it's just this. That's all, simple formula. What we're working out is speed of light, so V for velocity. Okay, how fast the light is traveling. Now, we've got 2 other symbols here we're going to use. F is the frequency. That one just makes sense, just like V made sense for velocity. This thing here, though, that might be new for you. This is lambda. This is a Greek symbol. Now, when we're talking about waves, this is the symbol we use for wavelength. Okay, so let's just run through a couple of things. First, frequency is measured in hertz. This is the unit. Okay, so the unit of frequency is the hertz. Now, what this actually means is how many waves are passing every second. So really, it's per second. Okay, that S looks a bit funny. There we go. So frequency is measured in how many waves per second, and we call that hertz. Now, lambda, the wavelength, it's a wavelength, so it's measured in meters. Okay, we should probably write that in wavelength. Now, what the heck is a wavelength? Right, well, let's look at a transverse wave. That is a really, really shocking diagram of a transverse wave. So, the eraser works. Let's try that again. Pretty bad, but that'll do. So, this is a transverse wave. So, the wave is traveling this way, and the medium, the stuff the wave's passing through, moves at 90 degrees to the direction that the wave's traveling, right? So perpendicular. So basically, if you had something here, it's going to be going up and down, okay, to give us this sort of wavy shape. Water waves out in the ocean or in a pond or anything, they're also transverse waves. It's just one of the types of wave. So what we have is, if we look at the top of this wave and the top of the next one, that distance from here to here is one wavelength. Okay, that is the length of one wave, and we could measure that distance in meters. We don't have to go from the top to the top. We could go from the bottom to the bottom, or actually, since this is science, the top is called the crest and the bottom is called the trough. So we could measure from trough to the next trough, and that distance will be the same, one wavelength. Now, we don't have to go from the crest to crest or trough to trough. We could go from any point on the wave to the next same point. So maybe we measure from here. Okay, we've gone past the trough, we're going up. So here, okay, we've gone past the trough, we've gone up about that far, and that distance is, again, one wavelength. Okay, so it's just the distance of from any point on the wave to the next same point on the wave. So that's our wavelength, and we actually measured this. We measured our wavelength as 12 centimeters, but of course we're not going to use centimeters. Well, that's in M. We're not going to use centimeters. That's not the SI unit. What we're going to use is meters. So we're going to use it as 0.12 so that we can stay in the SI units. Cool. What the heck is the frequency of the microwave? Well, to work that one out, you pull your microwave out of its little microwave shaped hole in the cupboards, and you look at the back and you see something like this. And what we're after is this RF output. RF stands for radio frequency. Now, we're not actually measuring the frequency of radio waves, we're actually measuring microwaves. It's a microwave oven, after all, not a radio oven, if that were even a thing. But they list it as RF, meaning radio frequency. That's fine. And here's our unit, Hertz. Okay, so, that tells us, yep, that's definitely the frequency, because there's our unit of frequency. And now the number we have for our frequency is 2450. However, those units are not just hertz, those are megahertz. Okay, now I've got another video dedicated to metric prefixes, right? So we've got K for kilo, right? That's essentially means times 1,000. Now, if we go up again times another 1,000, we end up at a capital M for mega. So mega is, well, I've gone up times 1,000 to get to kilo, and then times another 1,000 to get to mega. So actually mega is essentially meaning million, right? So we can replace that mega with 6 zeros. So 2,500 megahertz is the same as 2,500 million hertz. Okay, so there's our frequency. Cool. So we measured the wavelength. It was roughly 12 centimeters. pretty rough, but essentially it was about 12 centimeters or 0.12 meters. And the back of the microwave tells us that the frequency is very, very large. All right, this big number, 2450 million hertz. And now we can go and do our math, because remember our wave equation, the velocity of the wave is equal to the wavelength times the frequency. Okay, so now we just plug in our numbers. Let's do that. So we have our wavelength of 0.12 meters, and we times that by our frequency, 2450, with another 6 zeros on, because it was megahertz. So 2450 with 6 more zeros, hertz. And that gives us an answer of 294 with 6 zeros. Cool, there's our velocity, speed of light, yay, but that's actually not a speed though, is it? That's just a number. In terms of a speed, we need units, so meters per second. Now we know these are the correct units because this wavelength was in meters, and our frequency in hertz, but 1 hertz means per second. So when we put those together, we end up with meters over second, so meters per second. So that's the velocity that we calculated. Cool. Is that correct? No. Well, not exactly. It's pretty close though. So that's our experimental velocity of the speed of light. The theoretical value, what the textbooks will tell you, is actually 299, 792, and then a little bit more, 458 meters per second. So did we determine the exact speed of light? No. However, did we get pretty close? Yeah, I reckon we did. We use a chocolate bar in a microwave, for goodness sake. The measuring of that 12 centimeters, the 0.12 meters, that wasn't all that precise, was it? Sort of roughly from the middle-ish of the hole to the middle-ish of another hole, and it was pretty rough going. I was looking down through my phone at the time, so maybe it wasn't exactly 12 centimeters. Maybe it was a bit more, maybe 12 and a quarter, maybe 12.2. If it was something like that, that would actually bring our answer closer to what the theoretical value is. But, all said and done, I reckon that's a pretty good result. I'm happy with that. We got roughly 300 million meters per second. Okay, let's go to one significant figure. There we go. To one significant figure, yeah, it's 300 million meters per second, which is the correct value. So yeah, that's, I reckon, pretty good. Now, we call it the speed of light. When using light, we were cooking with microwaves. So really, we should call this the speed of microwaves, except we don't actually need to do that. If we go back to our wave, remember it was a transverse wave. Well, let's do this. Wait, let's not do that because that didn't do it quick enough. Let's do this. Start long, get quicker. Oh, closer. What we actually have is the EM spectrum, the electromagnetic spectrum. And this is a whole range of different types of radiation. What we start at radio waves, and then, radio and I guess TV are sort of mixed up in there. We go through microwaves. And then we have, what's next? Infrared. So infrared is what we actually feel is heat. You go outside on a nice sunny day and that lovely heat you feel beating down on your skin from the sun, that's infrared. And then we have visible light. That's great because we like to see things, so we use that to see all the time. UV, don't stay out too long in the sunshine. You might get sunburn. That's from the UV radiation, the ultraviolet. And then, oh no, I broke an arm, go and get an X-ray at the doctor. That's the next one. And then don't get mad and turn green because, you're the Hulk. That's from gamma radiation up this end, small gamma there. So we've actually got all these different types. Now, this visible light is actually a tiny, tiny, tiny fraction of the whole thing. But it's the EM spectrum. Now, firstly, we should say that all of these types of radiation travel at the same speed. So we used a microwave. We determined the speed here. This was actually the speed of the microwaves, not the speed of light, right? Not this visible light, except it's the same thing. All of these forms of radiation travel at the same speed, right? So back to our wave equation. This doesn't change. That is roughly 300 million meters per second for all of these.
Okay, so it doesn't matter if we're talking X-rays or microwaves or UV radiation or whatever, they're all traveling at the same speed, which we just call the speed of light, even though it might not be necessarily visible light that we're talking about. The spectrum part of the word means that one thing just changes into another. All right, so let's consider the colors of the rainbow. Roy G. Biv, right? How you remember the colors of the rainbow. Indigo, not really a color, but that's fine. So really there's 6 colors of the rainbow, but in terms of light, there are 3 primary colors of light. You've got red, green, and blue. But anyway, here are the 7 colors of the rainbow that Sir Isaac Newton gave us long, long ago. What we don't have is red here. And then there's orange here, and then yellow might be over here somewhere. We don't actually have that. What we do have is here is red, and it's looking a little bit orangey. It's actually more orange than red now. It's sort of really orange now, and now let's just call it orange because it's so orange. Okay, so we didn't have red in one place and then orange over there. We had the red becoming more and more orange, and now it's so orange that it is in fact just orange. And then the orange sort of gets yellowy orange. Now it's yellowish orange. It's both, and it's orangey yellow, and now it's just yellow. So this is what we mean by spectrum. One thing sort of becoming another, not discrete chunks. And that's what we have with the EM spectrum. So what could be changing here? Well, remember the wavelength. This, to the next crest, but then the next crest is closer, and the next one is closer, next one's closer, closer, closer. So our wavelength, right, that's a wavelength, that's a wavelength, that's a wavelength, it's changing. It's getting smaller and smaller and smaller. But remember, this velocity doesn't change. If the wavelength is getting smaller, that means the frequency also has to change. It has to increase, right? Because the wavelength and frequency are inversely proportional. As one goes down, the other goes up by the same factor, right? And that's what we see, because let's say at the speed this wave is traveling, maybe this represents 1 second. So here it's like, well, what's the frequency? Well, less than half a wavelength. It's not even 1/2 of a wavelength. But over here, the frequency is, oh, look, it's now a wavelength, trough to trough. And over here, it's a couple of wavelengths. Okay, so we have the different forms of radiation, one changing into another, so we call it the EM spectrum. But they all travel at the same speed, so that speed that we worked out of the microwaves is the same as the speed of the infrared and the radio and the X-ray. We just call it the speed of light.